properties nomenclature and then the reactions of. So when we talk about alcohols, what makes them the alcohol is the presence of the OH group, or we refer to this as a hydroxyl. So you're just going to stick a hydroxyl group onto an alkyl chain, and that makes an alcohol. All right. And so in terms of naming these guys, if they're quite simple, the naming of them is also quite simple, right? You just use the normal prefixes to identify the number of carbons in the parent, and then you just stick an OL suffix. So methanol for the one carbon alcohol, ethanol for the two carbon alcohol. This three carbon would be propan 2-all. All right. Notice when you start getting into more than two carbons in the chain, you do have to specify on which carbon the hydroxyl resides. Mhm. N-propanol would be on the one carbon. So N-propanol is just another name for propan 1-all. Okay, so let's go ahead and I want to talk to you a little bit about how alcohols are classified. All right. So we're going to use, we've seen this over and over again, this kind of primary, secondary, tertiary type style of classifying. Now, when it comes to the classification, what you're really looking at here is the carbon that is holding on to the hydroxyl group. By the way, that is also given a special name. We're going to refer to that carbon as the carbonyl carbon. The carbonyl is the one that's holding the hydroxyl. And so you want to ask yourself when you're trying to classify these, well, how many carbons is bonded to the carbonyl? So you can see in this first example that I highlighted here, the carbonyl here is bonded to only one additional carbon. So that's why we call it a primary alcohol. All right. Similarly, the one right here. There's the carbonyl I just highlighted. And it is bonded to one additional carbon. So that is also a primary alcohol. Now, if you move over, you can see in the secondaries, there's my carbonyl. In this case, the carbonyl is bonded to two carbons. So that's why it is a secondary alcohol. Same thing down on the ring. The carbonyl that's part of the ring in this case is bonded to two other carbon groups, and so it is also a secondary alcohol. And then moving to the last possibility, the tertiary case, the carbonyl here is bonded to three additional carbons, making it tertiary. And same thing over here in the ring. That carbonyl that's part of the ring is bonded to three additional carbons as well, and so it is also a tertiary alcohol. Now, if your OH group, if the hydroxyl group is on a benzene ring, that puts it into a different functional group class. All right. When you have a hydroxyl group on a benzene, we call these phenols. And the reason we put them in a different family is because they have very different reactivity, as we'll see later. All right. Questions there?
So all the stuff doesn't apply.
Correct. Yeah, it's a different, yeah, totally different thing. All right, so let's go ahead and look at the structure of alcohols. So as you can imagine, because alcohols, what what makes an alcohol the alcohol is that they have an OH group. Well, if you remember, anytime you have a hydrogen directly on an oxygen, it can hydrogen bond. And so it's just like water, right? So alcohols have that OH group, and so they have the ability to hydrogen bond with each other. All right. That will obviously affect the physical properties of these things. All right. So you can think of the alcohols as kind of they have a dual nature, right? Because that OH group wants to interact with water, right? It wants to hydrogen bond with water. However, you do have the alkyl part. Well, the alkyl part is nothing but CHs. And so that is a nonpolar component. So in these alcohols, you have both a polar region and a non-polar region. Right? So sometimes you'll hear this referred to as a hydrophilic, meaning water loving, versus hydrophobic, water fearing. Okay. Now, as you can imagine, if you have a small alcohol like a methanol or an ethanol, even a propanol, well, that hydrophobic, that non-polar region is relatively small compared to the polar part of the molecule. However, once you start getting into really long chain alcohols, that non-polar piece becomes much bigger and much more significant. So the bottom line is these alcohols will be water soluble if they're small. Right? If that non-polar piece is relatively insignificant. Okay. And the general rule of thumb is if you have 4 carbons or less, it'll be water soluble. Once you get beyond that, the non-polar piece becomes just too big, and it cannot be solubilized in water anymore. Okay. So again, bottom line is 4 carbons or less, water soluble. More than that, insoluble. Mm-hmm. Yeah. Yeah. Mm-hmm. Um, okay, so this kind of just shows you something that probably can already. Yeah, go ahead.
Sorry, I'm just a little confused. Wait, is that so? If a molecule would have multiple alcohols,
Mm-hmm.
would it be 4 per
Yeah.
alcohol? Okay.
Yeah. Mm-hmm. Okay, so this kind of just shows you something you probably already can know. Um, what you're looking at here is a series of 3 similar compounds. The only difference is this first one is all hydrocarbon, and so the only intermolecular force it has is the London dispersion forces. The second molecule, notice there's a chlorine now, that gives that molecule, chloroethane, a permanent dipole. And so this has London forces and dipole-dipole interaction. And then finally, with the alcohol, um, you have 2 polar bonds, namely the carbon-oxygen and the hydrogen-oxygen. All right. So this is going to have London forces, it's going to have dipole-dipole, but also has the ability to hydrogen bond. And notice the difference there in the boiling point. Very, very different. The stronger the intermolecular attractive forces, the higher the boiling point. Right. A couple of other things to notice. And we've kind of been alluding to this a little bit. The more OH groups you have, the more hydrogen bonding groups there are. And so the higher the boiling point. So notice the difference between the boiling point of this dihydroxy compound versus the single hydroxy compound. 197 versus 97. It basically doubles the boiling point. Right? Not surprisingly, the boiling point is going to increase with carbon number. right? And that's something that we've seen universally. If you have a longer carbon chain, your boiling point is going to increase, right? So for instance, methanol has a boiling point of about, say, 68 degrees Celsius. Ethanol has a boiling point of about 78. And then propanol, you can see, has a boiling point of 97. So as the carbon chain gets longer, the boiling point steadily increases. And then finally, like always, again, this third point is something we've talked about over and over again. Branching decreases the boiling point. Right? You can see that by looking at the comparison between 1-propanol and 2-propanol. 1-propanol is a straight chain, has a boiling point of 97. 2-propanol is a branched compound, and it boils down at 82. Mm-hmm.
Is there, there's a hydroxyl group take priority over so
Yeah, yeah, it will. Mm-hmm. A ring compared to a straight chain, rings will increase the boiling point because they don't have as much mobility, so they can pack closer together. Yeah, yeah, yeah. So if you compare, oh, I don't know it off the top of my head, but yeah, if you compare like hexane to cyclohexane, there is cyclohexane has a much higher boiling point. So yeah, rings will tend to cause the boiling point to be higher. Right? Okay. Um, so what we're going to look at now is the acid base um, nature of alcohol. So if you have a look, I have the ionization expression written here. So it is possible to take an alcohol, and if you have a strong enough base, you can remove the H of the hydroxyl. And that's just what's shown in this expression. When you do that, the conjugate base is what's known as an alkoxide ion. And this is a very common thing to do. It is not terribly difficult to deprotonate an alcohol and make the alkoxide. All right. And in fact, you can see I've got a couple alcohols shown. So here's water just for reference. You can see the pKa of water is 15.7. And a primary alcohol is very, very similar. It's very similar in structure to water, and thus it's going to also have a very similar pKa to water. Right? 15.7 versus 15.9. Now, there are a couple of things that are going to affect the pKa of these alcohols. Now, and one thing I always want you to keep in mind here is the real question is how stable is the conjugate base? The more stable it is, the more likely it will form. You know, another way of saying that, the more stable it is, the more likely it will form. Well, the more stable it is, the stronger the acid will be. So let's look at some factors that affect that. The first one, actually, before we do that, let's look at how to do that. The most, I've got a couple methods here. So you can take an alcohol and just add an alkali metal. That will deprotonate. Now notice, With a primary alcohol, you can just use sodium. But notice we cannot use sodium with tertiary or secondary alcohol. Now, I want you to see why that would be. I'm going to go back to this table for a second. So the primary alcohol has a pKa of 15.9. Look what happens as you branch. Like with isopropyl alcohol looks like this. That would be a secondary. And then tert-butanol looks like that is a tertiary alcohol. Look what happens as you get to the secondary and tertiary, the more substituted alcohols. Their pKa's are not, they're higher than with the primary. So the primary alcohol is more acidic than secondary and tertiary. And as a result, you need something stronger, something more active than sodium to deprotonate the higher order alcohol. No, the secondary and tertiary are less acidic than the primary. So that's why with this secondary and tertiary, you see we're using potassium. By the way, this also goes to explain, you think about all those E2 reactions we have been doing. Typically, when we are using a strong base for an E2 reaction, we were always using like sodium hydroxide, sodium methoxide, sodium ethoxide. But then our bulky base, it was always potassium tert-butoxide. Well, that is why. If you're trying to deprotonate a tertiary alcohol, it is a lot more work than it is to deprotonate a primary alcohol, like a methoxide or ethoxide. Okay. And it's, by the way, it's really easy to deprotonate the phenol. The phenol is much more acidic than a regular alcohol. The phenol has a pKa of 10. So that is significantly more acidic than any of the other alcohols. I do want to show you one final way, probably a more common way of deprotonating these alcohols is through the use of this base. And we're going to see this quite a bit going forward, this sodium hydride. Sodium hydride is really that is the hydride ion, H minus. And so what ends up happening is the hydride can grab the proton from the alcohol and you just generate H2 gas. So that is a very, very common method of deprotonating alcohol. All right, so let's look at some structural features that affect acidity here. Sterics are important. The more bulky the alcohol is, the less acidic it is. And that has to do with, so if you consider something like alkoxide versus tert-butoxide. Part of the reason why these ions can form is because they get solvated in solution. Right? Think back to that little cartoon you probably saw back in solution chemistry and Gen Chem. If you take salt and you put it in water, those sodium ions and chloride ions don't exist in isolation, right? The water forms a shell around the ions. And the same thing happens with these ions. So your water or whatever your solvent is is going to come around and try to surround or solvate the ion. And if you have something super giant and bulky, that is very difficult to do. The solvation is not as efficient. The solvent molecules can't get as close to the ion if it's super sterically hindered. And so this big bulky one is not as solvated and therefore not as stabilized. And so again, you can see that clearly illustrated by comparing ethanol to isopropanol, cyclohexanol to T-butanol. The more sterically hindered, the less acidic, right? Primary, secondary, and tertiary. All right. Okay, another structural feature that affects the acidity of these things is having is what we talked about this before, the inductive effect. Having electronegative atoms close to the negative charge will stabilize the negative charge. So what I want you to do here is look at the difference between ethanol, 2-chloroethanol, and 2,2,2-trichloroethanol. So let's compare each of those ions. So having those strong electron withdrawing halogens is making that carbon very delta plus. The more halogens you have, the more delta plus that carbon becomes. Well, that positive charge, or that partial positive charge, is going to begin pulling electron density towards itself. Remember, you have this big kind of electron cloud surrounding the O minus. And as you begin to make that neighboring charge, positive charge, more positive, it's going to start pulling the electron cloud towards itself. It's going to start to delocalize all of that electron density, or spread out that electron density towards itself. And the more you can delocalize a negative charge, the more stable it is. And so you can see through the pKa values here. Ethanol, it's got nothing. It's got no electronegative atoms nearby, and its pKa is 15.9. Put one electronegative group, makes it more acidic, 14.3. Put 3 electronegative groups, even more acidic, 12.2. Now, you can even go a step further. I'll give you one more just as a point of reference. if you have the trifluoro, that's going to drop it down to about 3.5 pKa. All right. So this inductive effect can play a significant role in the acidity of the alcohol. And then finally, the resonance effect. So this is kind of a direct comparison between cyclohexanol versus phenol. I mean, if you look at those two structures, look at the conjugate of those two structures, they might look very similar at first glance. Right? The conjugate of cyclohexanol versus the conjugate of phenol. But phenol has the ability to do something that cyclohexanol does not. All right, I can take the conjugate of phenol and draw a whole bunch of other resonance forms. Where that negative charge gets delocalized into the ring. So that would be one. And there's a couple more as well. So there's a whole bunch of resonance forms associated with phenoxide that other alcohols don't have access to. And again, the more you can delocalize the negative charge, the more you can delocalize the electron density, the more stable the structure.